So whenever you're ready, I can
Yeah,
start.
please.
Okay.
Started the recording, so we are good.
Okay. Hello, everybody, and welcome to the next talk in the series of our virtual seminar series under the Special Interest Group of AI and Machine Learning and Security with the TCCN. I am Subha Subbalakshmi. I'm a professor at Stevens Institute of Technology, and I'm also the chair of the SIG. And Dola Saha, who is from University of Albany, is the vice chair. So let me quickly give you an intro about the AI/ML Sec group. We are currently at around 413, just over 400 members in LinkedIn. And if you want to join us to keep updated with all of the things that we're doing in this special interest group, the LinkedIn group link is up here. You can also search for us under the name of IEEE AI and ML in Security Special Interest Group. Or you can, of course, email either of us, Dola or me. So, all right. So this seminar series started, I guess, with the pandemic in 2020, November, with Professor Vincent Poor's lecture being the inaugural one. And since then, we've got quite a few very well-respected speakers and researchers in this area, with our most recent one being Professor Bhaskar Krishnamachari, about whom I'll speak in a couple of minutes. But before that, just a few logistics. The recorded talks will be available at the SIG website, and that's the link to that is here. It'll also be available on the YouTube channel that we maintain. So that's also here. And we mute everybody on entry. We ask that you stay muted throughout the talk, but you can feel free to type all your questions that you might have in the chat box, even while the talk is proceeding, especially since it's hard to remember what questions came to your mind in slide number 15 when you're in slide number 52. So please keep posting your chats, that's fine. At the end of the talk, Dola will be reading those out for Professor Krishnamachari to answer them. So quickly, an introduction to Professor Bhaskar Krishnamachari. He is a professor of electrical and computer engineering at the USC Virabhi School of Engineering. He's also the director of Center for Cyber Physical Systems and Internet of Things. He works on design and evaluation of algorithms and protocols for wireless networks, distributed systems, and the Internet of Things. He's a co-author of more than 300 technical papers, 3 books, and collectively he has received, he's been cited more than 30,000 times. He has received Best Paper Awards at various really highly regarded venues, including IAPSN, Mobicom, and VNC. He is the recipient of NSF Career Award, the ASE Termin Award, and is listed in the MIT Technology Review's TR35 and Popular Science Magazine's Brilliant 10. So with that, I will let Professor Krishnamachari take over from now.
Thank you, Professor Subbalakshmi and Saha, for the invitation to speak. Is my set of slides visible yet or not yet?
Not yet.
Okay. How about now?
Yep.
Great. So, so I'm here to talk today about blockchain technology, particularly with respect to its applications to the Internet of Things. And this is an area that I got interested in about 5 years ago, mostly out of curiosity, trying to understand this new technology that's emerging, trying to understand what it is and what opportunities there might be to do research, both with respect to the technology itself and its applications, particularly to the Internet of Things, which was very much an area of interest to me over the years. So I want to start with just this note about why should academics be interested in blockchain technologies, and it goes by other names like distributed ledger technologies and so on. And so one way to think about what this technology represents is it's a new emerging domain of decentralized systems, which is a little bit similar to distributed computing or distributed systems, but somewhat different as well. And the key here is that you can think of it as a distributed system where the components of your system, your compute nodes, your network nodes, are actually spread across different administrative boundaries, economic boundaries, and trust boundaries. And often, when we think about distributed computing or distributed networking problems, often, although not always, these distributed systems are all within the same administrative domain. So you can kind of configure every element of it the way you want. There isn't really a trust issue within that single domain. But when you want to run your systems across multiple domains and you run into these trust issues and security issues that need to be addressed and economic issues that need to be addressed, and blockchain technology really pertains to this type of decentralized systems where there isn't a central single administrative domain that can control everything. The other reason to really explore the space is that with blockchain technologies, we're getting new types and combinations of value transfer, information, and transfer, as well as processing, that in particular pertain to how to do this type of a decentralized system that's crossing trust boundaries. From a research perspective, the reason I think academics should be quite excited about this field and engage more with it, for the past decade or so, a lot of the innovations in this domain have happened primarily through practitioners working in industry. And some of it is great and some of it is not so great. There's a lot of noise in that space compared to the signal. But there's still a lot for academics to do here, for researchers to do. And here's kind of a flavor of the types of problems we might encounter in this space, and just a few examples of those. One is a set of problems that have to do with how to improve efficiency, scalability, and sustainability. And I just realized that I haven't plugged in my laptop. Give me just 1 second. Just make sure I don't run out of power.
You also have a menu bar showing on the left. Left of the screen, okay. The menu bar. Yeah.
Got it. Is it better now?
Okay, now that's done.
Okay,
yes,
great, thanks.
That's good. Thank you.
Other types of problems here have to do with really providing some type of provable guarantees with respect to the privacy, security, and trust when it involves multiple domains. Third set of open problems have to do with taking this technology, understanding what its current capabilities are, and then developing and demonstrating its utility in new applications. And particularly in the context of IoT, we are used to looking at things like resource constraints and reliability issues and energy efficiency issues and so on. But at the same time, there's a lot of use cases for IoT that span across multiple domains, for example, in the context of IoT for supply chain and so on. So looking at how to develop this technology and see it in new applications is certainly an area that's very rich for exploration. There is in this space a need for new algorithms at every layer, and I'll talk about kind of a stack for blockchain technologies, but all the way from the core consensus protocols to programmable smart contracts and more. There is a lot of industry activity in this space, but they tend to be point solutions, and it's often unclear how they're connected to each other, how they can be generalized, how you can solve problems in other portions of that design space. And I think that's something academics can really contribute, kind of systematizing existing solutions, generalizing them, and also rigorously verifying them and identifying ways to improve on them. It's also a domain that attracts me personally because there's a lot of room for interdisciplinary collaborations between computer scientists, engineers, economists. You'll also run into people that have more of a perspective from, say, the political sciences or legal expertise when it comes to issues of governance of blockchain systems, or some of the legality around smart contracts and regulation issues in the space, et cetera. So I mentioned that blockchain technologies pertain to decentralized systems, and they're somewhat different from distributed systems. In fact, the core issue here was something that was known in the distributed computing literature for quite some time. Peter Deutsch had a list of 8 fallacies of distributed computing. And one of the items on this list was that there is one administrator. Everyone, when they're first building a distributed application, makes these assumptions. They all prove to be false in the long run and cause big trouble and painful learning experiences. And so moving from systems that are distributed but have a single administrator to systems that are distributed but with multiple administrators is actually a non-trivial task. And it's something that often gets overlooked in a lot of the traditional literature on distributed systems. So with decentralized systems, as I said before, we're talking about the movement of data, movement of computation across these different administrative and economic boundaries. And because it's going to cross these boundaries, you start to wonder about, can I trust the other entities that are part of this decentralized system? And what is it about it technologically that can give me that level of trust, security, and of course, increasingly also privacy issues? And so I do believe that blockchain technologies have a lot of a big role to play in the context of such systems. We'll see a little bit about it. I know that a number of you by now have encountered blockchain systems and might know quite a bit about it, but just to level set, very quick history. It goes back really to the original white paper that was posted by an anonymous or pseudonymous person or persons called Satoshi Nakamoto. And in fact, even now, I highly recommend for people who haven't looked at it to look at that white paper, because it sort of had a lot of the core ideas behind the technology in it. And it's very easy to remember how to find that paper. It's bitcoin.org/bitcoin.pdf. But Bitcoin, even though it was the beginning of the space of blockchain technology, is by no means the end of it. And there's many different use cases, a lot of technological innovation that's taken place since that first work. One milestone I might point out was the proposal to deploy Ethereum, which went from having kind of trusted transactions and records on a public ledger to also doing this type of decentralized computation on the blockchain, and introducing the idea of programmable smart contracts that can run on a blockchain in a way that gives you a level of trust and transparency into what computation is running. And then in 2016, there was Hyperledger Fabric, which is a permission blockchain protocol, which looks at use cases that are not necessarily anything to do with cryptocurrencies at all, and really have to do with collections of companies or enterprises working together in a consortium setting. And in the past 5 years that, for me at least, that I've been more engaged with the space, I've seen a number of innovations, both at the technological level, new consensus protocols, new primitives and building blocks for blockchain, but also interesting new applications that the technology can be used for, including most prominently decentralized finance, but also areas such as decentralized marketplaces, decentralized autonomous organizations, etc. So if you had to kind of look at the trajectory of blockchain technology, yes, the initial use case was about decentralized currency, and cryptocurrencies are still quite prominent in the narrative around it, at least socially. But going beyond just transferring cryptocurrencies, you can use blockchain technologies as a decentralized ledger that has certain properties, which I'll come to. And then with Ethereum and other kind of modern blockchain technologies also offering a layer of programmability, you also have decentralized computation. And so some of the attributes that, and capabilities that blockchain brings to the world is the ability to get some trust through decentralized governance. This can be a permissionless system where anyone can run a validating node, or a permissioned system where there's a set of nodes perhaps belonging to an industry consortium. You get the guarantee that the information that's stored on this public ledger of the blockchain, or that is being computed using this blockchain, is tamper-proof and immutable, and it is highly available. It is transparent by default, but if you want to make it more secure and private, there are mechanisms such as zero-knowledge proofs and encryption schemes that can be added on top of that. It is designed originally for kind of the low-friction transfer of digital assets, but also because of the programmability capabilities, it can allow you to enable and implement what are called credible implementations of game theoretic mechanisms, and I'll show an example or two of that. This is a overview of what I would call the blockchain stack, if you will. So at the very bottom, we have cryptographic building blocks that go into blockchain technology, everything from public key cryptography, hashing, Merkle tree, and other data structures that the information in a blockchain might be stored in. Digital signatures, we see the use of other advanced cryptographic schemes such as zero-knowledge proofs, verifiable random functions, etc. Often the very first thing you need to have in a blockchain system is some way to do Sybil control, which is to say that you don't want someone to be able to spoof multiple identities and have a high sort of a higher voice in the consensus process than they should. And in permissionless protocols, such as the original Bitcoin protocol, the way the Sybil control is provided is by forcing all the participants that want to run validation functionalities and adding transactions to the ledger to actually do some work that expends computational resources. So this is known as proof of work. And there are modern alternatives to proof of work that are less energy intensive, less using of electricity resources, and proof of stake is a good example of that. In fact, just recently, Ethereum has been merged into and is headed towards this proof of stake system. And another type of Sybil control mechanism, which is sort of the default easier one to work with, is called permissioned systems, where every node is explicitly authorized to be a validator node through some consortium, perhaps. Above this, we have the actual consensus mechanism for all of the nodes that are processing transactions and recording transactions or running computations to agree on the state of the ledger. And this is done through a number of different mechanisms. The original Bitcoin protocol has a consensus mechanism called longest chain adoption, but there's also a lot of traditional work in distributed systems that can be applied for consensus, such as various Byzantine fault-tolerant consensus protocols, and more recently, a class of gossip-based consensus protocols that have been developed. Above this, we can think about how is the data being structured and stored on the blockchain. It could be stored as a set of transactions in a block and a series of blocks that are hashed and chained together, which is kind of the data structure used in Bitcoin. But there are alternatives to this as well, including storing them in the form of directed acyclic graphs, which have other properties in terms of being able to partially order your transactions, but not strictly order them. Above that, there's a lot of work that is being done on improving the scalability of blockchain systems so that they can process larger numbers of transactions per second. And these go by names such as sharding and state channels, et cetera, or second layer solutions. Above this is the layer that I mentioned with respect to Ethereum, which is providing for programmable smart contracts. And sort of the core underlying computer science principle there is state machine replication, where every node that is running a virtual machine essentially stays in lockstep with every other node on the network, and they're all kind of moving through the state machine in a deterministic fashion as new transactions come in and get processed. And once you have this decentralized computation capability on the blockchain, you can then enable a large, rich set of applications on top, including additional tokens beyond the native token corresponding to that particular system, if it has one, various types of decentralized finance applications, Internet of Things applications, supply chain, etc. So the research that we've been doing in my group falls under a number of kind of related categories. We've done work on various decentralized protocols, both in terms of consensus mechanisms, as well as decentralizing IoT protocols such as publish-subscribe protocols, and I'll talk about these in the talk today. My group does do some work on decentralized finance as a particular application of blockchain technology, and there's a lot of room for sort of algorithmic innovations there. One of the areas that I'm going to spend a lot of time in this talk actually focusing on is the idea of data marketplaces. I think this is an area where blockchain technologies have a lot of promise and capability and a role to play. And we've looked at how to design such marketplaces, how to pay for data, how to ensure that that the data products on a data marketplace are of good quality through a decentralized review system, etc. And last but not the least, there are applications of blockchain to the domain of network security, and I'll say a little bit about it towards the end of the talk. And so I'm going to begin talking about decentralized protocols for IoT, then I'll spend a little bit of time talking about paying for IoT data, and then about data marketplaces and decentralized ratings. And then if time permits, I'll touch briefly on an application to network security as well. So when we talk about blockchain protocols, today they typically require that all the nodes that are validating transactions and adding them to the distributed ledger are online. And typically this means that they have to be wired, they have to be plugged into power, they have to be always on and connected to the peer-to-peer network. So one of the questions we've explored is, can we actually make wirelessly connected nodes, these could be mobile devices or even static IoT devices, to be first-class citizens in that validation process? And now the benefit of that, if we could enable it, is that the sheer number of nodes that could be brought on to help with the validation could be much larger. And so that larger number of validators can result in greater scalability of the system and greater security. And there's a bit of a trade-off between those two as well. It can increase the user adoption for blockchain protocols, and ultimately, it can make it potentially more applicable to IoT use cases. The challenge with this, the reason today's protocols typically don't allow mobile devices or IoT devices to do that validation functionality, is that these devices are, first of all, not always online. And so if you're trying to do consensus, but some of your nodes are on and some of them are not, can be challenging. And also because these devices tend to be limited in terms of their storage and compute power. So, so in this work called Blizzard, we actually looked at how do we potentially make wireless mobile devices a first-class citizen when it comes to the consensus mechanism. So this work called Blizzard actually builds on a prior protocol for gossip-based consensus that's been out there called Avalanche. And it basically aims to kind of scale up Avalanche by allowing for these additional layer of wirelessly connected nodes to be contributing to the consensus mechanism. So the basic idea of Blizzard is to have a two-layer hierarchy in the consensus process where there's a set of brokers, and the brokers are somewhat more a traditional type of a blockchain validator node. They're always online, they're plugged into power, they are connected to the internet, they form a peer-to-peer network with other brokers. And then we have this tier of other nodes which can be wirelessly connected, can be mobile devices or IoT devices. And now we're not going to make an assumption that the nodes in that lower layer are always connected or always on, but when they are connected and when they are on, they are randomly matched up with a set of brokers in the top tier. And that process of associating the nodes with the brokers also has to be somewhat randomized and changed over time to prevent collusion effects. But in particular here, the other assumption we don't make is that any node knows the identity or address of other nodes in the network because they're intermittent, there's large numbers of them. And so instead, the communication kind of proceeds in stages where new transactions that need to be validated are sent out by nodes to the brokers. They send out queries for validation responses to the other nodes, and the responses get aggregated back by the brokers and then dispersed to other nodes. And essentially, the consensus process proceeds through a gossip mechanism where over time, the nodes are kind of propagating their understanding of which transactions are valid to other nodes in the network. In order to prevent a collusion between the mobile nodes and the brokers, the particular mechanism that we employ uses a distributed random beacon. This is a cryptographic primitive that's become now recently practically available. And there's a way essentially to make sure that particular brokers on a particular round are connected to specific mobile nodes, that they couldn't control which nodes were connected to them. We actually, in this paper, one of the main contributions is to show that adapting the gossip-based mechanism to this two-tier protocol gives us some provable attributes of safety. So in particular, we assume some properties of nodes that are correct. And so we can have correct mobile nodes or correct brokers. And we also make some assumptions that the nodes as well as the brokers can also behave in a Byzantine fashion, some subset of them. And so the safety analysis boils down to how many of the nodes and how many of the brokers can behave in a Byzantine fashion before you lose some of the safety properties of the system. And what we're able to show in this work is that, typically when people talk about Byzantine fault-tolerant consensus protocols, you come up with a threshold, and it might be something like, so long as no more than a third of the nodes in the network are behaving in a Byzantine fashion, you can always achieve consensus correctly and safely. In the case of this two-tier system that we have, we're able to show that you end up not with a single threshold, but really a region in a two-dimensional space of the number of nodes, the mobile nodes that can be Byzantine, and the number of brokers that can be Byzantine, and essentially a trade-off between the two, where the more brokers are Byzantine, the fewer nodes can be behaving in a Byzantine fashion, and vice versa. And the region we show depends very much on the size of the network, how many nodes there are, how many brokers each node connects with, etc. We also present in this paper a methodology for analyzing the throughput and latency of a blockchain protocol. And the methodology turns out to be quite general and applicable to other blockchain protocols as well. Roughly speaking, what you have to do is essentially describe the sequence of events that every transaction has to go through until it gets confirmed. So you start with, when the first node sends that transaction to when it finally gets confirmed and logged in the ledger, what are all the steps that have to take place? And some of these are compute steps denoted here in orange, and some of these are communication steps that are denoted in green. And there's a certain amount of time that you take at each of these steps. And what you can show is essentially the bottleneck step determines the throughput of the protocol, and the sum of latencies of these steps determines the latency or the confirmation latency for the protocol. So it gives a way to kind of systematically characterize where the bottlenecks might be that affect throughput, and also what is the overall end-to-end latency for the protocol. So we're able to demonstrate that Blizzard has overall a lower latency, and we're able to characterize the amount of computation that's needed per transaction, the amount of energy that's needed per transaction, and show that that's feasible for more limited, resource-limited nodes to be able to do, and of course, scale how many transactions they can validate as a function of their compute power. And we're able to show that the system we're proposing is capable of achieving about 10,000 transactions per second, which is comparable to the state-of-the-art in the domain. The end-to-end latency, the moment a transaction gets submitted to when it gets logged in the ledger, is within a second. So that's really at the core consensus layer. Now I'm going to talk about the application of blockchain technology to decentralizing an application layer protocol for the Internet of Things. And many of us in the audience may be familiar with publish subscribe protocols that are widely used for IoT applications. A very common, well-known one is called MQTT. The idea here is that you can have a set of sensors that are acting as publishers. You can have a set of other devices or dashboards or compute points that are subscribing to data from publishers on a given topic. And there's a broker that the publishers send messages to publish whatever messages they have, and that essentially sends these messages on to the subscribers that are subscribed to the corresponding topic. Typically, an IoT pub sub system is centralized in that there is one server that's operating the broker, and there is no resilience in the system to that broker being malicious or manipulating the data flow in any way. So in particular, whichever organization or entity runs that broker may be able to withhold data from some subscribers, show them out of order to different subscribers in different order, or even tamper with the data in some cases if it's not end-to-end encrypted or otherwise protected. And so, and also the data itself, as it's persisted, may not be particularly reliable, may not be easy to access earlier messages, etc. And while traditional pub/sub protocols have been adopted and have a lot of uses, many of the real-world applications of IoT, particularly when you get to large-scale systems, this could be IoT systems for smart cities, it could be IoT used in the context of supply chain, you're going to end up with a large number of stakeholders that may not necessarily trust each other or may have vested interest if they were hosting the broker to manipulate the data flow, at least in some cases, and you wouldn't know for sure whether that has happened or not. And so to prevent this type of censorship or modification or manipulation by a single centralized entity hosting the broker, we would want to have a decentralized broker system. And so in this work on Trinity, published at ICBC 2019, we actually showed how a broker could be decentralized across multiple organizations. So multiple organizations run brokers, and there's basically a consensus mechanism that at the end of it can guarantee that all of the subscribers will see exactly the same verified stream of published messages in exactly the same order. And the way we do this is to basically integrate the standard MQTT brokers with a BFT consensus protocol. In our case, our implementation used a well-known protocol called Tendermint, and I'll mention a little bit about that. So the idea essentially is that there's a set of domains. Each domain hosts its own broker. Those brokers are connected to a consensus backend. The consensus backend then can be operating a distributed ledger layer as well for persistence. But independent of the persistence layer, the consensus mechanism essentially helps each broker know when a transaction has been validated, that a majority of the brokers or whatever is the threshold for the BFT consensus have approved this transaction and verified that it's a correct transaction, has not been modified. And you can be sure that everybody that's following that sequentially is getting exactly the same flow. The paper itself actually formalizes this notion and provides essentially a proof of safety and liveness for this protocol. But the key contribution is to allow us to decentralize any IoT pub subsystem like an MQTT broker across different organizations. We actually did an implementation of the system, as I mentioned, using MQTT as the IoT pub sub broker and Tendermint as the Byzantine fault-tolerant consensus layer. The architecture of the system, as we describe it, is actually agnostic in the sense that you could plug in other BFT consensus protocols or blockchain protocols on that side of it. And you can plug in other pub sub brokers, if there are alternatives to MQTT that one wants to use, one can do that as well. And all of this, of course, has to come at some cost. And we show that for Trinity, the delay, the end-to-end delay for the messages, the messages that you're subscribing to, does grow with the number of nodes, the number of broker nodes in the system, essentially linearly, empirically is what our results suggest. And intuitively, that's saying that as you're getting more security, because the more nodes there are in the system, the more nodes would have to be hacked and made to behave in a Byzantine manner in order to weaken the guarantees that are provided. And so the more nodes you have, the more secure the system is, but you're paying for it in terms of latency of the message. And so, and that allows potentially a trade-off in from an IoT perspective, where perhaps some messages that are more latency constrained and may not need to be secured as much could use a standard single broker or a smaller set of brokers, and messages that where the integrity is very important, but you're willing to pay for it with latency might benefit from the approach that's described here. Of course, this also opens up a research question of whether that latency can be brought down even further in an IoT setting where even the secured messages need to have lower latency. And so that's an open question to be explored. Next, I'm going to talk about paying for IoT data. Again, a lot of IoT systems initially have been designed where the entire ecosystem of IoT, from who owns the sensor devices, who's producing the data, who's consuming that data, and what you're doing with the data are all within the same organization. And that works for relatively small use cases, perhaps a single company deploying sensors on its factory to do measurements and analyze it. But over time, particularly in domains such as smart cities, we're going to see that the owner of the device is different from someone that can find a good use for it. And by allowing that data to flow from one organization to the other with less friction, we can actually enable a greater scalability for these IoT systems at city scale. But then you have to give the organization that owns the data some incentive to share their data with others. And often that incentive might be an economic incentive. And so that gets us to the flow of IoT data across trust boundaries, across administrative boundaries, across economic boundaries. And so how do we enable kind of this two-way flow of data from one organization to another while there's payments happening in the other direction? And can we do this in again, a frictionless manner in a way that gets implemented at the protocol layers rather than having to set it up, the common experience we all have, paying for data is subscribing to newspapers, right? How many newspapers or magazines can you subscribe to online? They all want your credit card information. And at some point, you don't want to sign up for too many of these. And that itself acts as a kind of friction. And the problem is that the web today doesn't really have an application layer protocol to make it very easy to pay for data on a per article basis or per packet basis, even if we can get it down that low. And so one proposal that we made in this regard is an application layer protocol called Streaming Data Payment Protocol, or SDPP. The idea here is that it's still a client-server protocol, much as most traditional data communication protocols are. So the seller here is operating a server. There's a buyer that's a client that would connect to the server to get the data flow happening. But in addition to that data channel, which is a traditional TCP and TLS type of transport channel, we also have a payment channel and a records medium where the payments could be done using a cryptocurrency or even a traditional payment rail, and the records could be stored potentially on a distributed ledger, which may or may not be the same blockchain that's hosting the payments mechanism. So the idea here is that you have a whole set of transactions that happen around asking the server what type of data do you have, this in having the server provide that menu of data items, making an order for a data item, getting that data, acknowledging that you got the data, the seller sending an invoice to get paid for that data, the buyer actually paying for it, getting an acknowledgement that it got, the seller getting the acknowledgement that it got paid, and all of this information getting kind of logged in a immutable ledger for potential later auditing and forensics if need be. So the point is to do all of this really at the application layer in such a way that every new application can just use the SDPP protocol without having to reinvent the data plus payments channels over and over again. So in this SDPP protocol, the way we've designed it, there's a parameter we call the granularity parameter, where you make payments for K data packets either in advance or after the fact, depending on whether you favor the seller or the buyer. But there's a parameter here that the number of packets that you're sending between each payment, that parameter, the larger it is, the less interruptions you're going to see in the data flow. But the smaller it is, the more you can manage the risk that the buyer could walk away without paying, or that the seller could take payment without selling. And so there's a bit of a trade-off between these, and intuitively, the download time, as we've measured empirically for SDPP, depends on that parameter. Things are much smoother when that parameter is larger, but then you're exposing yourself to higher payment risk. So depending on the use case, you may need to kind of adapt that parameter. Let me share a video. I hope the audio goes through. Just let me know if it doesn't. This is taking that idea of making payments for data, but also services, to the domain of vehicular connected vehicles. And so let me just play this video.
As they increase in autonomy, connected cars of the future will start to query the infrastructure around them to obtain data about navigation, electric charging stations, traffic, and more. As they encounter other vehicles on the road, They will share such services with each other and coordinate their actions in a dynamic and fluid manner. What is missing today is a decentralized platform that allows vehicles to autonomously negotiate and pay for these data services. Introducing Motive, a framework to enable micropayments for trusted vehicular services that has been developed by researchers at the USC Viterbi School of Engineering's Center for Cyber Physical Systems and the Internet of Things. Motive is a software running on each vehicle with several key components, beaconing to notify and listen to other Motive devices over the V2X radio. Link prediction to estimate the contact duration using privacy-sensitive navigation info. Scheduling of data and compute jobs between the vehicles. Payment using a blockchain-based wallet via cellular radio. And finally, rating of transactions by each vehicle. We now demonstrate the operation of a prototype of Motive we have built at USC. First, we launch and configure the demo by selecting parameters for the time until the vehicles come in range and how long they will stay in contact. The first vehicle then starts to beacon and listen for a beacon from another vehicle. When it hears a beacon from another vehicle that is in range, it detects and identifies the other vehicle and connects to it. It then checks that the other vehicle has a sufficiently high rating. Once validated, the vehicles exchange information about heading and speed to predict how long they will be in contact with each other. The two vehicles then advertise their services offered and needed to each other. The scheduling service runs on one of the vehicles to determine which services will be provided and in what order. In this case, the local vehicle is providing data about nearby EV charging stations to the remote vehicle. Upon completion, the remote vehicle makes a micropayment to the local vehicle using a blockchain wallet. Finally, both vehicles rate each other using a smart contract. Our design of Motive is inspired by the famous Internet hourglass architecture. Just as all Internet applications run on IP, and IP runs on any network, we envision that all future connected vehicle applications can run using Motive, and Motive can run using any distributed ledger technology, payment mechanism, and V2X communication system.
So in the SDPP protocol, we were having this parameter that determines how much risk the seller or buyer is taking on. We also wanted to look into whether that's even required, right? Can you set up a system with a smart contract that neither the buyer or seller has to take on any risk that the other party will not follow through, either in providing the data or in providing the payments? And this is a work that we published also at ICBC 3 years ago that looks at how a smart contract can be designed so that both the buyer and seller can be sure that on the buyer side that they'll get the content that they're paying for, and on the seller side that they'll get paid for it. And just to kind of back up for one second, what is the problem here? Imagine you were trying to transact with someone over email to buy a PDF of some book, perhaps. Now, if both parties don't know each other, don't trust each other, this can go wrong in one of two ways. The first is that whoever's selling the content could say, why don't you send me your payment first, and then I'll send you the PDF, in which case you could send over your payment and they could walk away without sending you the PDF. Or you could say, send me the PDF and I'll pay later, and you could take the PDF and walk away without paying, right? So in either case, there is this risk of not getting what you want. So we designed a smart contract that at the core of it is about a dual deposit escrow, where before the transaction takes place, both the seller and buyers have to place a deposit into the smart contract. Then they carry out some of the remaining steps. Now, in the interest of time, skip some of the details of this process and how various verification elements are captured in the smart contract. But the net effect of it is that if either party is unhappy, they can protest and essentially, not withhold their approval. And based on the verification, either or both parties' deposit might get slashed. And the fear of losing their deposit basically should make them behave honestly. There's some details of the protocol itself in the paper that I'd encourage you to check out if you're interested in this work. But we're able to analyze it using game theory and show that the only subgame perfect Nash equilibrium for this problem is achieved when both the seller and buyer behave honestly. And this is assuming both the buyer and seller are rational and not malicious. If you also are worried about malicious behavior, then by scaling up the escrow amounts sufficiently high, you can also dissuade malicious behavior, although that comes at the risk of creating more friction between the buyer and seller. So that's a work which tries to do away entirely with having to need specific, granularity parameter where you assume a certain amount of risk. It tries to make it a risk-free transaction, but it does require some deposits from both the buyer and seller. We've also worked on data marketplaces, particularly the question of how to ensure decentralized ratings. Traditionally, if you go to some online marketplace, maybe even Amazon or Yelp, you get reviews of products that you're interested in or restaurants you're trying to decide whether to go to or not. You have to somehow implicitly trust that the platform owner is not manipulating those reviews in any way, that they're not hiding unflattering reviews. And also you're hoping that the sellers themselves are not gaming the system by, posting fake reviews or by kind of posting negative unflattering reviews on their competitors' products, etc. And so the need for credible ratings is very important. And we kind of took this idea to a decentralized data marketplace on the blockchain. We had a paper in 2018 where we described kind of an architecture for a data marketplace that's decentralized and operated on a blockchain, various elements of it, and at least sketched out a vision for the research that needs to be done in this space. And so specifically with respect to ratings, we developed a scheme where it's very similar to the way papers often get reviewed for conferences. There's a random selection of anonymous reviewers, but in addition to selecting these reviewers anonymously, we also use test products and incentives to provide a check and balance on whether these reviewers are doing honest reviews or not. And we're able to implement such a scheme using decentralized smart contracts. And we're able to show that, again, through a game theoretic analysis of the smart contract design, that so long as the incentives are appropriately designed, the frequency with which test products are provided is sufficiently high, that any set of reviewers in a given setting have an incentive to actually do an honest review and not simply, rate a product without doing the work just to earn some income. And so it really ends up becoming a game theoretic mechanism design problem at the core of it, how the smart contract should be designed. And we're able to show that this should result in a higher quality product. And we're currently collaborating with Sony on a project that's looking at similar decentralized rating systems, but for NFT marketplaces, for example. I said I'd say just a little bit about applications of blockchain to security, and I just in the interest of time will say it very briefly. We have some work that's looked at how to use a blockchain protocol to create a software-defined network that is multi-domain, so that's operating across multiple administrative domains or organizations, where the authentication and access control framework is done using a blockchain-based system with smart contracts. And it allows network vendors and third-party service providers to securely set up their SLAs and enable stakeholders to audit network operations through a tamper-proof ledger. And there's a number of other directions one can take, the intersection of security, network security, and blockchain. For example, we have an ongoing collaboration with Chevron that's been looking at using blockchain to provide security for data transfer in industrial IoT systems. And I think, there's definitely a lot of interesting work to be done there. Finally, I think I'll just mention, because this SIG is focused on AI and ML, and I didn't say much about AI or ML in this talk, that there's sort of two classes of research that have been picking up in the last few years. And one of them is blockchain for ML, and the other is ML for blockchain. In blockchain for ML, it's using blockchain protocols to provide additional trust guarantees for things like federated learning and provide payment for providing data for machine learning models, etc. And then in the ML for blockchain domain, there's been an interest in questions such as, can you look at the data of transactions on a blockchain protocol like Ethereum and identify malicious entities or risky transactions that might be taking place there, and that could have certain financial applications as well. So I won't say a whole lot about that, but I just wanted to highlight that there is a lot of connections between AI, ML, and blockchain that are also just starting to be explored, and I think perhaps for some of the people in the audience that might be worth pursuing as well. So to conclude, I would say this is definitely an exciting time to be doing research at the intersection of blockchain and IoT. Whether it's resource constraints, connectivity issues, decentralizing solutions that tend to be centralized and cloud-based to being something that's suitable for a multi-stakeholder application, using Byzantine fault tolerance is something that blockchain technology can help with. A lot of questions that can be formulated as contracts or something that you want to do programmatically on the blockchain can be analyzed with respect to adversarial behavior using game theoretic analysis. And I think these are just a few examples. I'm sure as more people get into it from an academic perspective, the field's only going to get richer. If anyone's interested to learn more about our work, please check out our group's website. It's anrg.usc.edu. And there's a section on blockchain research where you'll be able to see some of the papers I've mentioned here. Finally, let me just do a quick pitch for a couple of books that came out this year, one of which might be particularly of interest to people that want to get kind of a breadth of what is the state of the art in blockchain technology, and that's the Handbook on Blockchain brought out by Springer just this month, actually. So I'll stop with that and take any questions. Thanks.
Thank you, Bhaskar. It was really an amazing presentation from a wonderful speaker. So our first question is from Suba. So maybe Suba, if you can chime in directly.
Yeah, I was just, I know you're mainly focused on blockchain, but I was kind of wondering if I can pick your brain a little bit on the rating thing that you said, where you were doing things using game theory. You are looking at ratings where the ratings are just provided, they are just numerical ratings. They're not descriptive narratives, are they?
So it's easier to analyze things that are quantitative. So in the first work, we were talking about numerical ratings where you can do things like, even if it's just a binary 0-1, is this good or bad? And you can say, I have a test product that I know should be above threshold, and is the rating kind of matching what is expected for this product? And then if it's subjective, of course, people will have different opinions on it. And ultimately you make a decision, possibly even for admission control into a marketplace based on that. In some of the ongoing work, we're actually looking at subjective ratings as well, text reviews. But then you also have other humans that are rating those reviews, that are upvoting or downvoting those reviews. So you get some signal about how good or bad those qualitative statements are. And you potentially, that's also a place where AI/ML could come in, is to do some sentiment analysis or other verification of the.
Yeah, we have been working on NLP and basically in the context of misinformation. So in a piece of text, can you tell if this is fake or not, if it's misinformation or not? And it has a strong tie into reviews. I mean, way back when, before we were doing it in this NLP type of way, we also used typical sort of statistical signal processing type techniques to just say whether a person is deceiving or not. So I was kind of curious about how your collaborations are.
Yeah, and actually, I mean, there's a very interesting connection there, because also at the same time, with the large language models now, they can submit reviews that are just AI generated that sound very compelling.
Yeah.
But to be able to filter out which ones are AI generated and actually the result of a genuine, careful review of the product might be, itself an interesting research question.
Yeah. Yeah, some of those things are the kind of things we work on in my lab. So that kind of piqued my interest. The other thing that piqued my interest, I don't want to.
Please go ahead. There are no questions so far, but please feel free to, from the audience, if you have any more questions, please feel free to post in as well in the chat. Yeah, please, Suba, go ahead.
Right. The other thing I was curious about was the scheduling that you were talking about in your vehicle-to-vehicle situation. Are you using a scheduling that's like a standardized mechanism, or are you looking at, did you develop your own scheduling mechanism?
Right. No, so the scheduling part of that is just a let's say a plug and play module that if you have a standard scheduling mechanism, you could just use that. Could just be first in, first out, could be prioritized in terms of the work or the payment or priority, etc. So yeah, there we didn't have any particular technical innovation.
Okay, so that's another thing that I was working on before I became completely into the NLP type things, which I'm not fully, it's not closed, the doors are not closed on that one. So we were looking at basically multi-axis edge computing. So looking at how can you offload computation of extremely complex programs that have their own program graphs or your call graphs, whichever way you want to call it. Which of these components would you schedule remotely versus locally, and through which interface through which you can connect, and
right.
what would be the relative data that you would be?
Yeah, and I think this is like a very classic edge computing problem, right? Distributed edge computing problem, where to run which task. Yeah. If you take those same set of problems people have worked on,
but not only with. So one of the things I find often that people don't look at is that it's also multi-axis, which means you're not switching between one type of axis or the other type of axis, but being able to distribute your across axis as well. Yeah.
And then if you also say that there's an economic piece to it, meaning that it's got different costs to the different options that you have. So, part of the scheduling optimization, you're also looking at maybe some cost objectives, et cetera. So that it can get quite interesting.
Yeah.
And potentially from a security perspective, also trust and reputation. If you have choices between two advertised compute points, one of which has a higher reputation versus another, would that factor into your scheduling decision and how?
Yeah. Totally.
Yeah. I see maybe another question there. Is that right?
No, that I think is Suba's question, right? Yeah. I have a quick question that is related to the computation. So we know that, yes, proof of stake is there, but what kind of work is going on in terms of distributing the computation itself? Is there anything that is going on where we can say that, well, there is a set of nodes who trust each other, and then the computation they together, can they become a broker itself? Just to distribute the computation, and then IoT devices can do possibly something on themselves. And I think
that is an area where I think academic research can shed a lot of light on alternatives to the way things are done today. The way things are done today is relatively simplistic. So a blockchain at its core doesn't actually do distributed computation for the reasons we do normally, which is to benefit from more compute resources to do things faster. In fact, it does quite the opposite. It repeats the exact same computation on every node, but for the sake of gaining security.
Right.
And so there is this, I mentioned sharding, which is basically to separate your blockchain itself, both the ledger and the computations across different shards to try and scale up the system at the cost of security. But also, somehow leveraging the distributed computing capabilities in each, within each shard, within each validating node itself. I don't see a lot of work on it. So I think that there's definitely, some room to explore how to make these things a little bit more efficient, and also maybe to treat different transactions differently. Not every transaction needs 100,000 nodes to, give it that level of security. Other transactions need it. And so, building a system that has a scalable notion of security, I think is another interesting direction.
Yeah, just like if I have 10 IoT devices, I'm sure that I have more IoT devices at home. Can they trust each other? And if there is a trust mechanism, can they share some of these computation among themselves, and they together can become one broker in of itself? So
Makes sense. Yeah. Yeah. No, I think that's not a direction I've seen explored a lot.
Okay, so we have another question from Julio Cesar Perez Garcia. So thank you very much for the talk. I would like to know what testbed you use to do the simulations. I'm a PhD student and it is a recurring problem.
So that's a great question. I mean, something we often run into as well. We did something very simple. For example, I mentioned this work on Trinity, which was about connecting MQTT brokers with a consensus backend. We have in my lab just a small test bed of 50 Raspberry Pi nodes that are all connected to a switch. It's relatively low cost, right? Raspberry Pi are cheap. We just have one big switch and we just plug them all into the switch so they can all talk to each other. And it turns out Tendermint, which was our choice to go for the BFT consensus protocol and blockchain mechanism, is lightweight enough to run on Raspberry Pi. And so we're actually able to use this test bed that's just 50 Raspberry Pi to run a bunch of experiments on. So that's definitely like a low-cost test bed I'd recommend if people are interested. In other work that we're doing currently in collaboration with Chevron, for example, we're actually doing this on the cloud. We set up virtual machines. We set up a Docker swarm of those virtual machines, talking to each other. And again, because it's all programmatically set up and torn down, you just have to create the containers once, and then you can kind of take it to your preferred cloud provider and run it there. So that might be a methodology that's also useful for this setting. Of course, that neither of these is an IoT test bed in the sense of collecting actual sensor data. We have other test beds that are deployed on campus to just collect sensor measurements that could be used for that kind of purpose. But often, our interest is less on the, let's say, the semantics of the data than the network aspect or the distributed computing aspect. So maybe that's less of an issue for us.
Great. So, yeah, thank you very much. Any more questions? Please feel free to write up in chat, or you can as well unmute yourself, because we have a very small group of people today. Unfortunately, we had another talk scheduled this morning on the same day, but for the whole TCCN group. And I think the two talks came up on the same day, back to back. So that's why we don't have a lot of people, but normally we see a bit more people here. So it got like clashed. So, so please feel free to unmute yourself if you have any questions. Okay. So this is coming from George Scalivantes. Good to see you here. Can you please share your thoughts on the application of blockchain on off-the-grid ad hoc wireless networks?
That's actually, a brilliant question, actually, because if you're not going to be even connected to the internet, it's an ad hoc wireless network operating somewhere, remotely away from the grid and, internet connectivity, then you have a different set of issues, potentially. The one project I can mention I didn't bring up in my talk that's kind of relevant to this is we looked at consensus and partition tolerant networks. So you have a set of nodes, they're going to be doing this distributed consensus and blockchain protocol, but that set of nodes is essentially like a DTN system, right? An intermittently connected mobile network. And so the set of issues there have to do, again, with some nodes are connected, other nodes are joining and partitioning it over time. How can you still run a consensus protocol if you don't have a single connected partition in the network? And so that was an example of a direction of research one could undertake. And I can imagine, doing something similar with blockchain on manets, perhaps, where there's sort of mobility resulting in disconnections in the network, and how do you kind of reconfigure some of that? Typically, blockchain protocols, if you have a single connected partition at all times, whatever manet routing protocols or anything you want under it, they can just provide an abstraction that allows you to set up a peer-to-peer network. Then most blockchain protocols can just work off the shelf. but they may not be working in the most efficient manner possible. So I think there could be some room for research to say, what does an efficient blockchain implementation look like when you have a mobile network underneath? To take that one more step, what if your mobile nodes are not all within the same administrative domain? One of my PhD students, Lily Clark, wrote a paper with colleagues at Aerospace Corporation when she was interning there that looked at doing MANET routing using a reputation system where you have a set of satellites. They don't necessarily trust each other to forward their packets, but they're building some reputation mechanism on the fly, and that's being logged to a ledger. And they kind of use the ledger to inform what is the reputation of other nodes in this ad hoc network, and then use that reputation to select routes that are more reliable. So I think there's a number of interesting directions there too one can explore.
Sure. Yeah. So Dr. Huang is saying that the earlier talk today was canceled due to technical difficulties and will be rescheduled. So we'll probably get to listen to that talk as well. So thank you. Yeah, so any more questions? If you have any more questions, please feel free to unmute yourself and ask. Otherwise, I will thank the speaker. Thank you so much. It was really a great talk. I learned a lot myself, and I hope that it was useful for the community as well.
Great. Yeah, and I'm happy to also take emails if anybody wants to reach out afterwards. Thank you.
Thank you.
Thank you.
Bye.
Bye.